evening and welcome to Tinkering with Edkelar. After the bunch of well-known meters, I thought I'd treat myself, and of course all of you out there too, to a bit more obscure kit. Recently I was browsing for second-hand electronics stuff and this little box caught my eye and just wouldn't let go. What is it? Well, that's a good question. From the markings on the panel, the sockets on the rear and the name, I guess it's a serial transmission line checker of sorts. It says Messempfänger, which is a measure receiver. The front dial has settings that include 1200, 4800, 9600, as well as 8 and 7, and a plus, minus or neutral switch. That all screams serial to me. What I can't say, however, is what exactly is being measured. The display has a percentage scale that ranges from plus minus 0 to 50 or 0 to 25%. So, let's find out what's inside. This assembly is rather easy. The front panel holds the PCB, but the screws are already missing. Once I disconnect the ribbon cable and power lines from the PCB, I can free the front panel assembly and take a better look. Lots of ICs, some transistors and resistors, and one crystal. 46 IC to be exact. The construction is typical for the 1980s. The rear panel says ÖPT 19810323, which means that this was either part of or certified by the Austrian phone company in 1981. I tried my best to find more information about this thing, but nope, nothing. The manufacturer, Datentechnik GmbH, is about as generic a name as it can be. It literally means Data Technology Limited. Guess how many companies on the internet have names like something something Data Technology Limited these days? The only clue I could find was a tiny reference in a RetroTech forum. The company specialized in handmade measuring and test equipment. That tracks. Oh, bubble LED displays and an LED bar graph. Nice! Since there isn't any documentation around and I don't like too much guesswork, I have to reverse engineer that thing. Oof! At least it's only a dual layer PCB and all the ICs are socketed, so I can remove them for easier continuity checks. I checked the supply rail and with 0 ohms, clearly one of the tantalums is shorted. I replaced that one since I don't have enough in stock to do them all. First off, I took a picture of both sides of the PCB and tried to trace the connections like that. Well, nope. The IC sockets obscured too much details. Next, I assign every component a number so I don't lose track. I start by mapping out the switches to their pins on the ribbon cables, which is when I realized paper is probably not going to be enough. So I moved to KiCad and created several blocks for whatever function I could deduct, like the power supply, the front panel PCB. But where it really became interesting is the actual signal input. Turns out that the serial port has the RX line connected and passed through between the two sockets, but not the TX one. So this is strictly a one-way instrument. Next, the CTS, DSR and DTR lines are held at plus 12 volts. Clearly, no handshake is implemented. Pin 10 on the modem side, which is listed as reserved for testing, is also held at constant negative 12 volts. The RX signal itself is then applied to a 100 kilo-ohm input resistor and transistorized input stage, which forwards positive and negative levels to optocouplers. The switch labeled 100K, 30K, SER is apparently the termination resistor. It parallels one additional resistor to the 100K one if needed. The SER option had me stumped for a bit, but it turns out that it just puts a full bridge rectifier across the input and ground with a 3.3 volt Zener diode across. So basically it will clamp the input to around 5 volts in either direction. No limiting resistor though. The optocouplers feed into a discrete flip-flop and thus give us a TTL signal as output. The next recognizable component was the clock generator. A rather simple quartz oscillator stage provides a 1.92 MHz base clock. 6 counter stages make for a whole bunch of derived frequencies, including odd divisions via a few gates and a reset input. We get as low as 20 Hz as an output. These various clocks are fed into selection chips, where one of them will become the output of the bunch, based on the selected rate of the front panel, but it's 200 times the selected value. That means picking 50 will give you a clock signal of 10,000. Oh, and the rear panel features a pair of banana sockets labeled Gen X. These are routed through a transistor and also fed into the clock selector as the external position. Makes sense. The front panel is pretty straightforward, not just in the literal sense, but multiplexing galore. The only special thing here is the center diode between the positive and negative range on the bar graph. It is shared and can be driven from either side via a set of diodes. Now here's where I'm drawing a bit of a blank. I followed all the lines around and connected all the dots, but it seems that the device is just counting. Not quite sure what. The number of bits might be selected with the 5678 switch. These are connected to a programmable countdown chip as selected value +1, which triggers at 0. Also, this is where somebody goofed and we have a botch in the diode logic. In between getting cross-eyed with following traces, I decided to try the timing circuit to confirm at least that one. And yes, the clock is divided up and put onto the output in what I call the pre-scaled clock. Back to the circuitry. The core of the thing seems to be 2 counters in decimal mode, which will count from 0 to 50 maximum, since the second one uses an if 5 feedback to the clock circuit signal. They are clocked with the pre-scaled clock, the direction is tied to the bit counter somehow, and the reset is done with the in data section flag. The resulting values are fed into the bar graph logic for display and also into a latch that is coupled with a set of comparators. Putting the stuff back on the rear panel. Connecting the wires again. and giving the transformer a quick try. The front panel takes a bit of tweaking so that the LEDs are straight, the switches are vertical, and all the rotary positions line up. While tightening down the reset switch, I heard a rather alarming crack. And indeed, the case of the switch was crumbling. These old plastics are brittle, and with the switch soldered in place, it had no way to turn. I have a similar switch around, but the guts don't quite fit into the new case. This one has an on and maybe option. That means a solid on one side, off in the center, and a momentary one on the other side. So, playing the crazy glue and 3D puzzle game it is then. Well, that worked out better than expected. I added a layer of epoxy on the outside too for additional mechanical stability. This time I don't tighten down the switch as much. Let's just hope that nothing falls off over time. And after putting in all the ICs again, a quick power on test. Yay! Oops! I don't think it's supposed to go out. Yet another tantalum cap shorted out. And after another 2 tantalums, they are polarized, I finally have lights. The test button causes all the LEDs to turn on, at least briefly. Darn! One of the segments in the bubble LED is gone. That's annoying. Now for some testing. I wired up the HP serial tester to run a looping simulation, and indeed, the A and Z LEDs correspond to mark and space on the RS-232 line. Sweet! Z might be for Zwischenraum, which is brute German for space. But I can't really think what mark would become as A. Let's not glance over the fact that I still have absolutely no idea what exactly this thing is measuring. I shuffled around my schematics a bit, double-checked some suspicious connections and arrived at the conclusion. It measures stuff. Timing stuff, to be more precise. I can't be 100% sure, but it seems that the plus-minus side will indicate transitions in the input signal that are either too early or too late when compared to the set data rate. That would explain why it runs at 200 times the expected clock. Since the HP tester only provides pretty exact timing, I decided to put in a rectangle signal from my signal generator, and indeed, if the signal is off and doesn't quite align with the expected frequency, it gets all sorts of deflections on the display. Now, the case is in pretty good condition, but it has a few scratches. I'll just go over it with a layer of similar paint to hide the worst of them. Finishing up the case next. The cover was a bit tricky to close. The case has little slide-in plates with threads for the screws, but these are loose and I had to glue them in place first. No idea how that would have worked originally, but it is very much annoying now. What I can confirm so far, the start-stop setting picks a start condition either on the first rising or falling edge that the device sees. Isochr, maybe isochrone, that doesn't seem to care about start or stop and it just counts, whereas the sync-int just aligns the incoming edge with the internal clock and also always counts. The code setting is giving the number of bits that the device counts in start-stop mode. After the expected number of bits, it stops. The toggle switch, plus and minus, tells the counter what edge to count, rising, falling, or both. I also confirmed that the counter will only count up to 50, matching the 25 LEDs. The 7-segment display is a peak counter and the bar graph will show the current value directly. That means it will flicker quite a bit if the result is unstable. The 25-50 switch switches the bar graph from 1/2 the value, or 2 counts per LED, to the lower 25 range for 1 LED per count, cutting off the top edge. The reset button is for resetting the peak values in the number display. With manual, it resets immediately. With automatic, it resets some seconds after the last peak has been seen. The number of seconds can be changed with a jumper bridge on the PCB. Mine came with 12-second intervals. And that's it. Quite an exercise in reverse engineering and understanding slightly odd integrated circuits. I enjoyed it very much. Of course, in a more modern design, pretty much all of the ICs would be one PIC or microcontroller, but where's the fun in that? If anybody out there has a proper manual for that thing, or maybe even worked with one, please let me know. I would love to actually read useful values from it. I hope you enjoyed this rather deep dive episode. See you next time! A rather simple quartz oscillator provides a 192.